counting proper colorings. Recap of previous lecture. We have discussed the Brooks theorem and some properties of critical graphs. Content of this lecture, we will discuss the properties of counting function, is also known as enumeration of the colorings in a graph. We will also see the chromatic polynomial, chromatic recurrence and other further important enumerative aspects of coloring. So, the chromatic number chi of g is the minimum k such that the count is positive. Now, knowing the count for all k would tell us the chromatic number. The counting problem was also used to tackle the 4-color theorem. In this lecture, we will discuss the properties of a counting function and the classes where it is easy to compute and other related topics. So, counting proper coloring is represented by a notation which is basically chi of g and another parameter, that is called k. K is, we will explain k. So, k is any natural number and a given graph G, the value, the chi of g k is the number of proper colorings. So, you know that proper coloring is represented by a function f which will label the vertices from the set of label, that is the k set of labels are given. These labels are called colors because the values are not important. So, the set of available colors is k. We can represent either them in the form of labels 1 to k, or we can also say that k different colors. So, the k colors need not all be used in the coloring using this particular mapping function f. So, changing the names of the color that are used will produce different colorings. So, we have to count how many such different colorings are possible here using this particular notation, that is chi of g comma k, and that is nothing but enumeration of the colorings possible with k different colors in a given graph G. Let us consider an example. In this example, we will consider a graph which is the complement of a complete graph. So, if the complete graph is k3, so k3 complement graph will look like this way, that 3 nodes are there. So, complement means in the complete graph they have an edge, in a complement of that particular graph they do not have any edge, although only the nodes will be present. Now, if you are given a color k different colors, so let us see that a particular node we can choose any one of these k colors. So, there are k possibilities to color the vertex number 1. The second vertex is not connected. So, again we can pick any of these k colors and there are k possible ways to color the second node. Third node is concerned, also it will basically require any of the k colors. So, third node. So, if there are n nodes, so all the nodes will receive the same color. So, total number of colors is nothing but the multiplication of k n times. So, the chi value of complement of a complete graph with k different colors, the complete graph with n nodes will have k raised to power n different chi value. Another example of this counting is, so if you are given a complete graph, let us say here the n is 3, so we are given k3 and we are also given the number of colors as k. So, we want to find out the total number of possible proper k colorings. So, let us take the first vertex. So, since we are given k different colors, none of them are already used. So, the first vertex will be colored using any of these k or k different ways. Now, having utilized the one color, the remaining will be k minus 1 different colors available. So, the second vertex can be colored with the remaining k minus 1 different ways. So, having used another color, so the remaining colors will be k minus 2. So, the third vertex can be colored with these k minus 2 different colors. So, there are k minus 2 different ways. Hence, the chi value is represented. So, if there are n nodes, so k minus n plus 1 will be that particular result. Now, so this will tell these are the number of ways to color a n vertex graph with k colors. Now, before we go ahead, let us see another important thing. Now, if we give a less number of colors, and with that less number of colors the proper coloring is not possible, what will be that particular value? So, let us take k2, complete graph of two vertices, and we are given only one color. So, if we use one color, the second color if we try to use, then it will not be a proper. Why? Because the other vertex is the adjacent vertex and it has to basically cannot use the color which is already given to its neighbor. Another color is required. So, chi value of k2 with one color will become 0. Why? Because there is no proper coloring. Now, if we increase the number of colors by one more, that is 2, then let us see how many ways we can color it. So, it is one color and the other color we are going to give it to the other one and vice versa. Similarly, if we are having, so let us plug it this particular formula here. So, k into k minus 1, so k is 2 into 1, that becomes 2. So, hence 2 colors are required. Now, k2 if it is having 3 colors, then what will happen? So, the first vertex we can color with, so that becomes k minus 1. So, k is 3 into 2, that is 6 different ways we can color if the number of colors are more, that is 3. So, this is important that if the number of colors is less than the minimum required colors, then obviously the chi value will become 0. So, when coloring the vertices of kn complement, we can use any of the k colors at each vertex, no matter what color we have used at the other vertex. Hence, since each of these kn functions from the vertex set to kn is a proper coloring, hence we have already told. Now, when we color the vertices of kn, the colors chosen earlier cannot be used on the ith vertex. So, there remains k minus I plus 1 choices for coloring the ith vertices, no matter how the earlier colors have been chosen. Hence, this particular formula we have already derived. Now, we can count this also, k choose n and factorial n means there are different. If we change the names of the colors, then we can obtain different orderings. So, hence this is the number of ways to assign the colors. Now, we have already seen that if there are 3 different colors, then the first vertex is colored with 3. So, we can apply this particular formula that k choose n is 3. So, 3 choose 3 times 3 factorial. So, 3 factorial, this becomes 1. So, 3 factorial is 6. Similarly, 4 choose 3 and 3 factorial. So, this becomes 24. The value of the product is 0 when k is less than n, that is the number of colors k is less than n. This makes sense since k has no proper k colorings when k is less than n for the complete graphs. Now, proposition, if T is a tree with n vertices, then chi of T with k is equal to k times k minus 1 to the power n minus 1. Now, let us see the proof and then we will see the example. Proof says that choose some vertex v of a tree as a root. We can color v in k different ways. If we extend the proper coloring to the new vertices as we grow the tree from v root at each step only, the colors of the parent is forbidden and we have k minus 1 choices for the colors of a new vertex. So, having colored this particular root, when it comes to the descendant, we can color with the remaining k minus 1 colors, similarly to this also, to this also. Now, when we go to the next level, here also we cannot use this color. So, the remaining is k minus 1. So, k minus 1, k minus 1. So, if a tree with n nodes is given, so the first node we can color with k different ways. Having used one of these colors at the root, then the next level can be colored with k minus 1, and if there are n different such nodes afterwards, so this will be the total number of ways we can color a tree of n nodes with k different colors. Let us take an example. Let us take this particular tree. So, here n is equal to 6 and let us say that number of colors are given k is equal to 2. So, first we can color with the number of colors. Now, then we can use the other level with a different color. We cannot use red, then red again we can use here. So, we require another color. So, next level we can use this particular color. So, two colors will basically color them. Let us see the formula. So, the first vertex 2 times, second is 2 minus 1 becomes 1 times n minus 1, that is 5, that becomes 2. So, this is this particular tree T with 2 colors, only there are 2 ways. Now, if the number of colors is equal to 3, let us see how many ways will be there. So, the root node we can color with 3 ways and the remaining nodes, that is n minus 1 different remaining nodes, can be colored with other 2 ways. So, what is the value of n here? N is 6 minus 2, that becomes 4, 2 raised to power 4, 3 multiplied by 2 raised to power 4. So, that will be the result here in this particular. Now, we see the chromatic polynomial. Chromatic polynomial is another way to count the colorings and is to observe that the color classes of each proper coloring of G partitions vertices of a graph into independent sets. Grouping the colorings according to the partition will lead to a formula for chi of g with k coloring, that is polynomial in k of degree n. Note that this holds for the answers in the examples which we have seen earlier, since every graph has this particular property as a function of k is called the chromatic polynomial of. Let us see the proposition. Let x is equal to x, x minus 1 and so on up to x minus r plus 1, and let PR denotes the number of partitions of the vertices into R non-empty independent sets. Then chi of g with k is nothing but the summation from R to n PR times kr, which is the polynomial in k of degree n. Let us see this, and we will take an example to show this particular polynomial. Now, when R colors are actually used in proper colorings, the color classes partition vertices of G into exactly R independent sets, which can happen in PRG ways. When K colors are available, there are exactly KR ways to choose the colors and assign them to the classes. All proper colorings arise in this way, so the formula is correct. Now, KR is the polynomial in K and PRG is the constant for each R. This formula implies that chi of G with K is a polynomial function of K. When G has n vertices, there is exactly one partition of G into n independent sets, and no partition using more than that set lead to the leading value is k raised power n. Always Pn is equal to 1 using the independent set of size 1. So, P1 G is equal to 0 unless G has no edges, since only for Kn complement is the entire vertex set is an independent set. Let us consider when graph is C4. Now, there is exactly one partition into two independent sets. This is one independent set, this is another independent set. So, independent set will have, this is the partition 1, this is another partition. So, let us say that A, B, C, D. So, one is A, D, the other partition will contain B, C. So, it has only one partition. So, opposite vertices will be in the same set. When R is equal to, this particular, when R is equal to 2. Now, when R is equal to 3, R means number of independent sets are 3. So, now we can see 3 independent sets means this is one independent set, second one, and this is third one. So, A, B, then C and D. So, when R is equal to 3, the independent sets will be AC, then B, and then D. So, we put two opposite vertices together here, we have shown you, and leave the other two sets in the set by themselves, that we have done. So, we can do this in two different ways. So, two different ways means either this way or the other way. So, the total number of ways to do these kind of partitioning when the independent sets size is 2, there is only one way of doing it. When independent set of size 3, we have seen here there are two ways. When independent set of size 4 means all are isolated. Now, let us see the polynomial according to the previous relation. So, when the independent set of size, one independent set of size 1 is there, independent set of size 2, there are one way. So, 1 into, there are k ways to color one independent set. So, having chosen that color, we cannot use that color, the same color. So, the remaining colors will be k minus 1 and we can color it to the independent set. When the total number of independent sets are 3, so there are two ways to do this, and let us count how many colors, how many ways we can color this 3 independent sets. So, the first independent set we can color with k, having utilized one color, the second independent set will be k minus 1, third is k minus 2. When the independent set is of size 4, then basically only one way is possible, only one way can have. Now, let us see the colorings of 4 different independent sets, k, k minus 1, k minus 2 and k minus 3. So, if we solve this particular equation, it comes out to be which is shown over here. Now, computing the chromatic polynomial in this way is not generally feasible, since there are too many partitions to consider. So, there is a recursive computation much like that used in the counting of trees. Again, we have to see the background for building it, that G dot E is the representation for a graph which is obtained by contracting an edge E. So, if this is the graph which is called a kite having this particular edge, so G with this edge is contracted, when edge is contracted, that becomes a particular vertex where this edge will not be present, but these edges will be present. So, that becomes an graph. Since the number of proper k colorings is unaffected by multiple edges, we may discard the multiple copies of an edge, hence this becomes the graph, keeping only one copy to form this kind of graph. So, with this particular introduction of the contraction operation in the graph of an edge, given edge E, we now define a theorem which will give you the chromatic recurrence. So, chromatic recurrence theorem. So, if G is a simple graph and E is an edge in the edge set of that particular graph, then the chromatic value G for k different colors is equal to chromatic number of G without that edge with k different colors minus chromatic number of G contracted an edge E with k different colors. So, the proof will give you the idea. Let us see this particular proof. Now, every proper k coloring of a graph is a proper k coloring of G minus E, that is the graph without that edge. A proper k coloring of G minus E is a proper k coloring of a graph if and only distinct colorings to the endpoints of V. Hence, we can count the proper k colorings of G by subtracting from G minus E with k the number of proper k colorings of G minus E, that gives U and V the same color. Now, colorings of G minus E in which U and V have the same color correspond directly to the proper k coloring of G contraction E, in which the color of the contracted vertex is the common color of U and V. Such a coloring properly colors all the edges of G minus E if and only if it properly colors all the edges of G. Let us understand this concept. Now, if this particular graph is given, then if we remove this particular edge, these vertices, if they have the different colors, then that many number of ways in which they are different, that is to be subtracted. So, again why? Because let us see that if there is an edge, then basically this will receive a different colors. One is, let us say, blue, green, the other is another color, let us say purple. Now, if we remove this particular edge, if we remove this edge, then there is no need of different colors. So, maybe that we can use the same color in this particular graph. So, we have to find out the graph without this edge, which is having the different colors, that is to be calculated and removed from it. So, again I am repeating the proof, so that will be indicated over here. So, every proper k coloring of graph G is a proper k coloring of G minus E. So, if k colors are used here in G minus E, and if the edge is not present, then basically if the edge is removed, then basically the number of colors are going to be reduced. So, the proper k coloring of G minus E is a proper k coloring of G if and only if it gives a distinct colors to the endpoints. Hence, we can count the proper k colorings of G by subtracting from G minus E with k colors the number of proper k colorings of G minus E that gives V and E the same color. So, here we have to remove this many number of colorings which give the same color to U and V vertices. For that we will do the edge contraction, hence this particular formula is derived. Now, let us see how many colors C4 produces with K using this particular formula. So, C4 is this one. So, this C4 we can, if we can remove this particular edge, this will become C4, this will become P4. C4 minus one edge is P4, proper k coloring of P4, wherein both are basically having the same color is to be removed if we want a proper k coloring of G minus E. So, that becomes that if we contract that particular edge, if we contract that edge, that becomes a vertex, and that is nothing but the triangle. So, chi of G with k colors is chi of this vertex with k colors minus. Why? Because then it will reduce the number of colors. So, how many cases where both are getting the same color is to be removed. Now, you know that what is the value of path P3 with k colors is nothing but first vertex. So, it is nothing but a tree. So, tree will say that k times how many remaining is 4 minus 1, that is 3, minus, as far as this is concerned, triangle. So, the triangle will require like the complete graph. So, k, then k minus 1, then k minus 2, and if you solve this particular equation, k into k minus 1, that is k minus 1 square minus k minus 2. So, that becomes 3, and this becomes minus 3k, minus 2k and minus 2k. and this becomes k square. So, hence this particular equation we have derived. Now, because both G minus E and G contraction E have fewer edges than G, we can use the chromatic recurrence to compute GK. So, we need initial conditions for the graph with no edges, which we have already computed here in this case. So, theorem. Whitney in 1933 has given a theorem for chromatic polynomial. Theorem: the chromatic polynomial chi of G with k of a simple graph G has a degree ng, with integer coefficients alternating in sign and beginning 1 minus e, then plus, and so on. Let us see the proof of chromatic polynomial. So, we use induction on the number of edges, on the edges of a graph. So, the claim holds trivially when the edges present in the graph is equal to 0. So, if there are no edges, then this particular recurrence is basically nothing but the complement of kn with k, that is nothing but k raised to power n. For induction step, let G be an n vertex graph with Eg is greater than or equal to 1. Now, each of G minus E and G contraction E have fewer edges than G, and G contraction E has n minus 1 vertices. By the induction hypothesis, there are non-negative integers ai and bi, such that the chromatic polynomial of G minus E with k is equal to the summation of I, which is running from 0 to n, minus 1 raised to power I ai times k with the power n minus I, and G contraction E with k, that chi value is equal to summation of I is equal to 0 to n minus 1 with minus 1 raised to power I bi times k n minus 1 minus I. So, by chromatic recurrence, both these equations we will see that chi of G with k is equal to chi of G minus E with k minus chi of G contraction E with k. Now, let us see these in turn, that is nothing but k raised to power n times E g minus 1 minus E g minus 1 times k n minus 1 plus a 2 k n minus 2 and so on, I minus 1 to raised to power I ai and k raised to power n minus I, that we have seen in the previous slide. Now, another, there is a term for edge contraction, it has to be subtracted. Now, you know that with edge contraction the number of nodes will be n minus 1. So, here for nth node there will not be any polynomial leading term. So, the leading term will start with n minus 1, k raised to power n minus 1 minus b 1 times k n minus 2 plus and so on up to I minus 1 raised to power I minus 1 times b I minus 1 times k n raised to power k raised to power n minus I. So, if we subtract both these recurrence, equation 1 and equation 2, so 1 minus 2 we will get the recurrence for our desired formula. So, kn will come over here and this particular term, both factor will be incorporated. So, here it is minus 1 and plus 1, so that becomes Eg. So, this term, these terms are verified. Similarly, we can include a2 and So, minus and minus they will becomes plus and so on. So, finally, minus I and this is AI plus BI. So, this will be basically taken care of, minus and minus they will become plus. So, hence chi of g comma g with k is a polynomial with the leading coefficients a0 is equal to 1 here, and the next coefficient is basically minus a1 and plus b2, that is nothing but minus eg that is present, and its coefficients alternates in the minus sign. So, 1 minus e, then basically then again it will be plus 1 and then again it will be minus and so on. So, these signs will alternate in this particular manner. So, when adding an edge yields a graph whose chromatic polynomial is easy to compute, we can use the chromatic recurrence in a different way. Instead of saying that gk is equal to g minus e with k and subtracting with g contraction e, we can write down instead of that g minus e is equal to, that means this term we basically put on the right side, that becomes both plus. Now, this you know that this way also we can compute. Let us see that we want to compute this kn minus, this is kn minus e, that is e is present, e is absent. So, let us include it and we will form this particular recurrence. Similarly, here with contraction this is kn minus 1. So, we can solve this particular recurrence. Why? Because we know that this is easier to produce, this is also easier to produce, and hence this is another example how we can, instead of saying that an edge is to be removed, rather than we can say that edge is added and the contraction operation. So, we close our discussion of chi of g comma k, that is the number of enumeration of the colorings of a graph G with given color K with an explicit formula. It has exponentially many terms, so its uses are primarily theoretical. The formula summarizes what happens if we iterate the chromatic recurrence until we dispose of all the edges. So, there is another theorem given by Whitney in 1932. Let C of G denote the number of components of a graph G. Now, given a set S which is a subset of the edges of G, of edges in G, let G of S denotes the spanning subgraph of G with the edge set S. Then the number, that is chi of G with K of the proper K colorings of G, is given by this particular equation, that is nothing but the summation of the subsets of S of edges with minus 1 raised power that subset S times K raised power C, that is number of components in subset of, in a spanning subgraph with S. So, in the proof, if we see that in applying the chromatic recurrence, contraction may produce multiple edges, we have observed that dropping these does not affect the chi of G with K. We claim that deleting extra copies of the edges does not change the claimed formula. Let E and E prime be the edges in G with the same endpoints. When E prime is in S and E is not in S, we gave that number of components of G S union E is equal to number of components with S, since both the endpoints of E are in the same component. However, S union E is nothing but the cardinality of S plus 1, thus the terms of S and S union E in the sum cancel. Therefore, omitting all the terms for the set of edges containing E prime does not change the sum. This implies that we can keep or drop from the graphs without changing the formula. When computing the chromatic recurrence, we therefore obtain the same result if we do not discard multiple edges or the loops. and instead retain all the edges or contraction or deletion. Iterating the recurrence now yields 2 raised to power e time e terms as we dispose of all the edges. Each in turn is deleted or contracted. When all the edges have been deleted or contracted, the graph that remains consists of an isolated vertices. Let S be the set of edges that were contracted. The remaining vertices correspond to the components of GS. Each such component become one vertex when the graph of S are contracted and the other edges are deleted. Let C of GS isolated vertices at the end yields a term with k raised power number of components of GS colorings. Furthermore, the sign of the contribution changes for each contracted edge. So, the contribution is positive if and only if the cardinality of S is even. Thus, the contribution when S is the set of contracted edges is -1 to the power cardinality of S times k to the power number of components of G with the spanning subgraph of S, and this accounts all the terms in sum. So, let us take example of a chromatic polynomial. When G is a simple graph with n vertices, every spanning subgraph with 0, 1 or 2 edges has n, n-1 and n-2 components respectively. When S is equal to 3, the number of components is n-2 if and only if the 3 edges form a triangle, otherwise it is n-3. For example, when G is a kite with 4 vertices and 5 edges, that is shown in the diagram, there are 10 sets of 3 edges. For 2 of these, GS consists of a triangle plus 1 isolated vertex. The other 8 sets of 3 edges yield spanning subgraph with 1 component. Both types of triples are counted negatively. Since S cardinality is 3, all spanning subgraph with 4 or 5 edges have only 1 component. Hence, the theorem yields k raised to power 4 for this particular graph, k raised to power 4 minus 5 times k raised to power 3 plus 10 times k square and so on. So, that gives the same formula that we have earlier proved. So, this agrees with the earlier stated computation method by counting different colorings directly without using this particular formula, by using this particular way. So, basically we can see that chromatic polynomial is a direct method of application without doing all enumeration steps in between. Whitney proved in the theorem using inclusion exclusion principle of elementary counting. So, letting AI be the set of k colorings, assign the same color to the endpoints of EI. We want to count the colorings that lie in none of these AI to AM. So, in this lecture we have discussed the properties of counting function, chromatic polynomial, chromatic recurrence and theorems based on these issues. Thank you.